So in the previous lecture we discussed a single stage flash drum in which we had a feed pressurized to certain pressure, high temperature, then it was flashed, and then we had this separation between vapor and the liquid phases, and then we drew this Txy diagram, we had the projection on Hxy diagram, we wrote the species balance, material balance and enthalpy balance to show that how does the tie line on Txy diagram is equivalent to the tie line on this Hxy diagram, and essentially we marked the salient features on these diagrams, Hxy and Txy diagram, and we also said that one can apply the mixing rule between the two streams, two living streams which are in equilibrium, vapor and the liquid, to show that the feed also lies on the straight line lying between vapor and liquid. Okay. So in that example or that short discussion we had in the earlier lecture, we said that this flash drum is equivalent to an ideal stage of a distillation column in which two living streams can be assumed to be in equilibrium. In other words, if we give enough residence time and we have enough good mixing between the two phases, vapor and liquid, then we can assume that the two living streams are in equilibrium, and Yx or Hx, Hy, they will lie on this tie line. Okay, but very often it happens that the two living streams are not in equilibrium. So in that case, it's also important that we understand what happens to the tie line, what is the movement of this tie line as the two living streams are not in equilibrium. Okay, so we continue with the discussion. We will have a qualitative discussion of this non-equilibrium on Txy as shown in Txy and as shown on this enthalpy Hxy diagram. Okay, so just recall, we had this flash drum and we had this feed F ZF HF. All right, it was brought in this brought to heater. We had this heating load Q. Okay, certain pressure P1, then it was throttled or flashed to this pressure P2. So the molar flow rate remains the same, ZF remains the same, except now the enthalpy of this liquid is HF plus Q, or if this Q is in calorie per second, then we can have HF by F. All right, so HF by F, or excuse me, we can have HF, we have calorie per mole plus Q by F. So Q is nothing but say calorie per second heating rate here, and then we have this vapor living D, YD, HD, and we have this liquid living here, flow rate was W, molar flow rate W, we have XW, and we have this HW. We said that this L vapor here and the liquid, they would be in equilibrium if we allow for good mixing and sufficient resistance time. So if they are in equilibrium, we can have this Txy diagram, and the coordinates of this Y and X, they will lie on this tie line, or we have a horizontal straight line corresponding to this temperature T, at which the liquid composition, saturated liquid composition is X and saturated vapor composition is Y. So it's an equilibrium, and if we take this projection on Hxy diagram, then we showed that we have this X, Xy, and we have H, liquid enthalpy and liquid vapor, and then corresponding to these 2 points we have this tie line, which is Y here and X here. So the same mole fraction they appear, and this is a tie line on this Hxy diagram, this is a tie line on this Txy diagram. Now what happens if these two living streams, they are not in equilibrium? Now in these cases we can have several cases. All right, so if we have two streams living, liquid and vapor, not in equilibrium, then let's see what scenarios we can have. So we have this TXY diagram. Now the one thing that can happen, that the vapor and the liquid, they may not be at the same temperature. In other words, we have this mole fraction given X here at this temperature T1, but vapor may be slightly smaller than this temperature that would have been at the tie line. So instead of this, now we have this kind of situations. Also, we can have an equilibrium where it is possible that the temperature is the same for liquid and vapor, but the compositions are different. In other words, we can have a situation like this, in which the composition of liquid is X, but the composition of vapor may be slightly smaller than this. So these are different scenarios of non-equilibriums. In one case, we can also have the other way around, when the coordinates for the vapor phase lies on the saturated, this dew point, all right, like this. This is your Y, but the liquid mole fraction is slightly smaller than what would have been had this been under equilibrium. So instead of this, now we have this situations. So in other words, we can have all types of scenarios, right, for this non-equilibrium. Two living streams, not at the same temperature. Okay, so on the tie lines, we don't have this horizontal straight line. Now vapor is here, or liquid is here, and vapor is here. Or this could be other one. There's some difference in temperature between the two living streams, not the same as the flash drum temperatures. Or in some cases, it's possible that we have the same temperature, but Y and X, they do not correspond to this tie lines. Maybe mole fractions in the liquid phase is slightly larger, or maybe the vapor phase is slightly smaller, and etc. We can have several of this non-equilibrium conditions. In the case of non-equilibrium conditions, then it's very important that we understand that when we take the projection on HXY, then what line we will get, it won't be a tie line either. Okay, so we draw this TXY diagram, or we draw XY diagram equivalent to this non-equilibrium conditions. So if we have Y and X, and recall we took this 45-degree line, then we take this projection of X here like this, and we take this Y like this. So we have this Y here, and then this line will fall on this equilibrium curve YXY diagram. However, if we have this non-equilibrium, that means the temperatures are different, then you can see that when you go down to this, and when you come here, then it's possible that this point will not lie on this equilibrium curve. All right. Similarly, we have this feed line. So if you recall that earlier we had this ZF. Okay. Now we have ZF here, and now for the equilibrium curve, and if there is non-equilibrium, then we can have this tie line slightly moved away from this. Similarly, if you plot HXY diagram, okay, so if you plot HXY diagram like this here, and recall we took the projection for Y, we took the projection for X, we have this XY on this tie line here. But again, if mole fractions is different, or mole fraction is the same but the temperature is different, then one can show that this feed ZF which we have here, it's possible that we have different conditions like this, or we can have the conditions like this. So in either case, it's possible that what line we obtain by taking the projections from here and X, they will not be a tie line. In other words, this point will not lie on this equilibrium curve. So these are the different things which we have to remember for equilibrium conditions and for non-equilibrium conditions. All right. Now what we do, we start the second topic, that's the distillation column. All right. So what we have done so far, TXY diagram, HXY diagram. Just in case of absorptions, we establish the thermodynamic solubility diagram. So now we have this equilibrium, vapor liquid equilibrium, assuming we have the two living streams are in equilibrium, etc. Now after that, we started this flash drum. We said the flash drum is nothing but a model. This would be a founding stone for our design of a distillation column. So in that case, if you have one stage, then two streams, they come to that stage, they mixed, well mixed, and then they leave. So the living streams can be assumed to be in equilibrium if we talk of ideal stage, etc. All right. So now we take up this design of a distillation column, or how do we get number of trays required for achieving certain degree of separations, either in the vapor or in the liquid phase. Now there are two different approaches. One approach is based on Txy or Yx for a given temperatures, okay, and the second approach is based on Hxy. If you recall that, we said that once you fix the temperature, mole fraction x and y, then the enthalpy is fixed. In other words, two methods are more or less identical. So approaches are different. In one case, you work on enthalpy, you do the enthalpy calculations, and in other case, you work on mole fractions x and y balance. Both of them should give the similar answers to find out how many number of stages we require. One method is called Ponchon-Chevret methods, HXY, and the second method, which is based on mole fraction TXY diagram, that's called Maccabé-Thiele methods. Okay, Maccabé-Thiele method is more popular, more convenient to use. Okay, but there is a very strict restriction or assumptions one has in this Maccabé-Thiele methods. Enthalpy HXY methods is more cumbersome mathematically or calculations, okay, graphically, but it's more rigorous. Okay, so we start with HXY diagram, which is based on Ponchon-Chevret method to determine the number of stages in the distillation column. All right. So we have this method here, which is Ponchon-Chevret method. So we are going to work on this HXY diagram, and we said although this method is cumbersome, but it's more rigorous than the other methods. So what is a distillation column? Schematically, the way we drew for absorption column, we have a tower like this, vertical towers, and there are trays. All right, so there are several trays like this. Okay, and we have a feed here. So we have several trays. Feed is brought here. So say the molar flow rate of F, feed is F moles per second. We have the mole fraction ZF. Again, let's focus on binary components A plus B. And we have the enthalpy given as calorie per mole. Okay, so this is the coordinate of your feed. This feed is brought into this distillation column. Say the pressure is fixed at PT. Okay, now at every stage, if you look at, so there are several stages like this. If you look at every stage, what physically scenario we will have, liquid will trickle from the top. All right, it will go like this. So there's a pool of liquid here, pool of liquid, and the vapor, it will go through this. So there is certain layer of this liquid in which incoming liquid and incoming vapor, they are allowed to come and well mixed here. Then the leaving stream is a vapor here, and the leaving stream is liquid here. Now if you recall our discussion on this flash diagram, if it's an ideal stage, which means we have the equilibrium between vapor and the liquid, and if the mole fraction is y here and the mole fraction is x here, then this y and x will lie on this Txy horizontal, this tie line, or in this case of HXY diagram, if you recall, we will lie on this tie line. So both are the tie line if they are in equilibrium. For this chapter, we assume that each stage or trays, they are ideal stages. Okay. Now this vapor, this feed gets in. It has a certain mole fractions. Now you can take a there are several trays here. Then you can draw where each stage the vapor is leaving. Okay, and we have the liquid getting in here, trickling from the top. Okay, now let's concentrate on the top phase. When the vapor leaves here, then this vapor is taken outside. We have a condenser here. Vapor is condensed. So there is a condenser load drawn by this downward pointing arrows to show that certain calorie per second is released from the system. So the stream which comes out from here, it's condensed here, then we have a separator, or we have some storage here. We will discuss about this. So liquid here, so let's say this entire vapor is now condensed into this liquid, then part of this liquid is brought back to this distillation column, and that's the liquid which you see here trickling down. So there is a reflux, and part of the liquid is your product. So this is the product. All right, let's erase this. So we have feed F, and we have the top product, which we call it D for distillate. So this distillate will also have composition ZD, and it has enthalpy. All right, reflux is liquid. We call it L0, we denote by L0. It will also have the mole fraction XL, X0, and the enthalpy is 0. Now notice here, if entire vapor is condensed to liquid, then the compositions X0, ZD, and the compositions of the vapor which is arriving from here, Y1, flow rate G1, enthalpy HL1, Y1, X0, and ZD will be the same. All right, enthalpy HD will also be same as HL0, and these enthalpies will differ from HL1 by this QC calorie per second. Okay, so this is what we call it total condenser. In the total condenser, we have Y1 same as ZD, same as X0, because the entire vapor is now condensed, so the mole fraction does not change. And the enthalpy of reflux liquid which goes back to the distillation column is same as the enthalpy of the living vapor, this liquid product. So this product is liquid. All right. Now let's talk about the certain nomenclatures here. Generally we follow the number of plates. We give the counting starting from the top. So we have this 1, top plate is 1, then we can have 2, 3, etc., and say we have a small n here. Similarly 1, n, n plus 1, and this will continue like this. We can have m. All right, we can have somewhere say m plus 1. Similarly we can have this n plus 1. Okay, another plate here, and the top plate, bottom plate is n. So there are total number of plates are n here, 1 to n, 1, 2, 3, 4, n, n plus 1, then we have m, m plus 1, and finally we have this n here. The reason why we have given the two different nomenclatures, n and m. Actually the sections ever feed from here, this is called as rectifying sections. So this is rectifying sections. Why rectifying? Of course we can make out the feed, the one which is one component out of A plus B, which is more volatile, the vapor will become rich in A. So we are saying that this stream is getting rectified, this stream is getting purer and purer. So product ZD has mole fractions much larger than what we have ZF for component A, which is more volatile. Similarly, the liquid which trickles from the down will become richer and richer in other components B. So section just below F, this is called as stripping section. Two together is distillation column. All right. Now let's see what happens to the liquid. Liquid which leaves from here, now it comes to a reboiler. All right. Here we are giving the heat, call it QB. So notice this QB and QC, this is a condenser. Okay, and now we have this Q boiler, where this liquid is vaporized and vapor sent back to part of the vapor, this part of the product stream feed is sent back to this column as a reflux, and we withdraw this liquid part of the liquid here as a bottom product, which we call it residue. So W, XW, HW. Similar to we have distillate D, ZD and XD. Okay, so essentially we have a distillation column consisting of two parts, rectifying section and stripping sections. Underneath F and above F, we have a condenser where we take the top product vapor, condense, take out the product, part of the product is sent back to the distillation column called as known as reflux. Okay. In the stripping sections, we say the liquid is getting richer and richer in A, so the product XW will have the mole fractions A, which will be much smaller than what we have A here, or the mole fraction of B 1 minus XW, which will be much larger than this B. So essentially we have stripped A from here and we are transferring it to this vapor phase. So we have rectifying sections and we have this stripping sections. Okay. Reflux R is defined as called external reflux. External reflux or reflux ratios. This is defined as L0 over D. So if you withdraw 100 moles per second and send back say 20, then reflux ratio is 20 by 100. Okay. So that's the ratios of molar flow rates of L0 and D. That's one thing. Here we have the reboiler, we are giving the heat here, and then we withdraw this liquid product here, and we have this part of the liquid is vaporized to send back as a reflux here. So we have the liquid reflux here and we have this vapor reflux here. Okay. Now we'll also have this nomenclature G. So let's look at one stream, one plate, say N. So notice the difference that we are using M for stripping sections and N for rectifying sections. So N represents a general plate number N counted from the top 1, 2, 4, 5, Nth, and we are counting it N plus 1, say 46, 47, M and M plus 1. So if you look at N, that means we are looking at a stage, a general stage in rectifying sections, where we have a vapor stream which comes from N minus N plus 1 stream, because we are counting from here. So the vapor which arrives at N comes from N plus 1, and this vapor N, it goes to N minus 1 plate. Liquid which comes from here, that's from L minus 1, it comes to the Nth plate and it goes to your N plus 1th plate. Okay. We give the nomenclatures here L, this liquid which leaves from Nth plate, it is Ln. Vapor which leaves from Nth plate is given the nomenclatures Gn. So Gn and Ln, they are in equilibrium. This would be Ln minus 1. This would be Gn plus 1. So Gn, then we have Yn, then we will follow this, we'll call it Hgn. We have Gn plus 1, Yn plus 1, Hgn plus 1. Alright, so the convention we are following that the streams are tagged with respect to this plate they originate. So this vapor originates from here, this nth plate, so it has Gn, Yn, Hgn. This vapor originates from the bottom plate just underneath this N plus 1, so it gets the nomenclature Gn plus 1, Yn plus 1, Hgn plus 1. The liquid which originates from this N plate, the leaving, it's Ln, Xn, and we have HLN. Alright, and the liquid just above this is Ln minus 1, we can write Xn minus 1, you can write HLN minus 1. So this is nomenclatures we are following it. You can also take a plate, just for continuing our discussions, plate number M. Alright, so which means this vapor which is arriving here will have the nomenclatures given as Gm plus 1, Hgm plus 1, and we have Ym plus 1. Similarly, this would be Gm, Hgm, Ym. G stands for gas or vapor. So that's the conventions we have for this. And so forth, we can have the argument for the liquid streams which trickles or falls from the m minus 1 stage and leaves to this m plus 1 stage. Again, these two streams are in equilibrium. Okay. Now what we do here, we talked about this condenser. So before we do some more calculations, let us concentrate on one more time on this condenser. What we described in the previous slide or the previous page here, we said that the vapor which arrives from here, the top. So notice that this composition is again Y1. Why? Because the top plate is the first plate 1. So the vapor which leaves from this, originates from this plate, is Y1. Molar flow rate is G1. Mole fractions or enthalpy is given is Hg1. All right. Now we are condensing it here. We said that in the previous case, entire vapor was condensed. So that's the case 1 we should write. We should make a note that case 1 we have total condenser. So we condense the entire vapor. As a consequence, if you recall and revisit the page, the leaving product, the liquid, and the leaving and the reflux which goes to the column has the same compositions because we have just condensed, so the composition will remain the same here. Now the case 2 or the arrangement 2 is called partial condenser. So a typical distillation column can be run in either of the two modes. So we understand that what happens in the partial condenser. Now when we have the partial condenser, the way we draw this schematic here, that now we condense partially, which means this vapor, some products are still left out. So now notice this here, we call it, still this is a D distillate, but now the mole fraction is Yd instead of Xt. Why? Because it's a vapor phase and the enthalpy is Hd. Liquid which is condensed now this goes back as a reflux. Notice this is molar flow rate is L0. Why 0? Because the top plate is 1 and this plate is actually 0th plate outside the distillation column. Okay, so this reflux will go back to this column top of this plate. All right, so this comes from one plate above this. We'll talk about it, we continue. So this is L0, mole fraction is X0 and enthalpy is HL0. Now notice here that this vapor and this liquid, the two living streams, can be assumed to be in equilibrium. So see the difference. In the earlier case when we had the total condenser, this Zd or Yd or Xt, it was same as X0. But here Yd and Xt represent equilibrium mole fractions of vapor and the liquid. So you can think that on Txy diagram they will lie on this tie line, on this Hxy diagram they will lie on this tie line. So in the partial condensers, living mole fractions of distillate D is in equilibrium with the reflux. In the total condenser, two compositions are the same. Hd and HLO, it's a saturated vapor enthalpy, it's a saturated vapor liquid. And also notice that here that Y1 will not be same as Yd or X0. One has to make this species balance to find out how Y1 is related to Yd and X0. So it's very important that we understand what happens to the living stream, compositions, enthalpy and the vapor in case of total condenser and the partial condensers. So this here we have two living streams in equilibrium. So actually this condenser can also be considered as a theoretical stage. Theoretical stage in case of partial condenser, because two living streams are in equilibrium and we call it 0th stage. So in addition to all these nomenclatures and conventions which we are using here, we also important to understand that mole fractions Yd and x0, they are not the same here. Okay. So now let's just summarize qualitatively. We have a distillation column, so it's a vertical column. It consists of several trays, plates. These are, we'll talk about in subsequent lectures, plates, or you can go to the textbook to see that. Plates are nothing but it has sieves, like sieve plates. There are different type of configurations. Mostly our discussion will be confined to the sieve plates. So we have the plates, circular distillation column, plates like this, and there are uh, holes on this sieve plates. So the idea is that the vapor will flow through the plate. There will be a pool of the liquid. So vapor will essentially bubble through this pool of the liquid. Liquid head is maintained constant with the help of a downcomer, etc. And the liquid falls from the top. So entire distillation columns, let's say there are several of plates. Feed enter at some locations, not necessarily at the middle of the distillation column. Feed can be inserted, or feed can enter into the column, much below the midpoint. We'll talk about this when we take up the design. Where is the entry point of the feed? So feed has certain compositions, say 30-40, 30-70, and we want to enrich 30 to say 90 for A, and the bottom product rich in B 70 to 90 again. So it's possible. So one enthalpy, one feed molar flow rates, mole fractions brought into this distillation column. There's a vaporizations at every stage. Vapor which enters the pool of the liquid meets with a different liquid which is non-equilibrium. They mix, spend some residence time, then the vapor leaving and the liquid leaving, we can assume them to be in equilibrium if it's an ideal stage. Now vapor leaves from the top column, top plate, it goes to a partial or total condenser. So we have a condenser where we extract the heat. So enthalpy is reduced there. If it's a total condenser, then the mole fractions leaving from the top plate and the mole fraction of the product and the mole fraction of the reflux will all be the same. Enthalpy will be different. Okay, enthalpy of the leaving product and the reflux will be the same again, but it will be different from the incoming vapor phase to the condenser, and they will differ by this condenser load. Liquid, so this all section above feed we call it rectifying sections, and the sections just underneath feed we call it stripping sections. We discuss why. Okay, now the liquid gas trickles down, flows down, comes to a reboiler because we have to send the reflux back again to the column. So the part of this liquid is withdrawn as a product. What product we want? W, moles per second, and part of this liquid is vaporized and sent back to this column. So again we have this QB, this heat goes into the system. So certain heat is removed, QC, from the condenser, and certain heat gets into the system. So there is a temperature gradient. You can think that temperature will be larger by intuitions at the bottom, and slowly this will decrease here. Hydrodynamically, pressure will also change in the distillation column because vapor and liquid, they have zigzag path. Vapor has to overcome the hydrodynamic resistance. Liquid of course falls through by this hydrodynamic. But for our design calculation, we assume that pressure more or less remains the same. In other words, we make use of the fact that given pressure, distillation pressure, whether atmospheric or larger than atmosphere, Txy diagram and Hxy diagram are available to us. Okay. So this is about the introductions to the distillation column. We understand the meaning of this reflux. There is an external reflux ratios inside. Certain part of the liquid gets inside. So we have L0 by D, external reflux ratios, how much amount of total product is brought back. There are some cases where the entire total reflux is, it's 100%. So those are very extreme cases. But so far, let's be familiar with our conventions of G, L, M, N, stripping column, rectifying column, reflux ratios, partial condenser, total condensers, right? Before we make a species balance, enthalpy balance on several envelopes. So we will cut a sections above the feed all the way till the condenser. We will take another section just underneath the feed all the way till the boiler. We'll make this energy balance, we'll make this species balance, and we will see that how we can track the coordinates of the mole fractions, how we can track the locus of these mole fractions in the vapor phase and the liquid phase as the vapor flows up and the liquid flows down. So let's make enthalpy balance, species balance, material balance on certain section of this distillation column. Okay, we'll have to take several envelopes. So okay, so before that, let's redraw this distillation column again. So very quickly, we have this distillation column. Let's just mark the top plate, which is 1. Let's just mark the nth plate, which is N. Vapor withdrawn from here. Let's have total condenser, the simpler one. We have QC, condenser load, calorie per second is withdrawn. We have this separator, and we withdraw this product or distillate, D, ZD, HD. We have the reflux, L0, X0, HL0, and it goes back to this distillation column. So we have Y1, H, G1, and we have here G1, because all of them, this vapor comes from this top plate. So similarly at the nth, we have this Gn plus 1, Yn plus 1, Hn plus 1. All right, and this liquid which comes from here is Ln, HLN, and we have this Xn. And this liquid, the reflux, this liquid composition, and the stat is the same as, status is same as the reflux here. Okay, so now let us make a balance on this condenser. So we will write the balance equation for this condenser. Okay, so if we look at, maybe we have taken the envelope like this. We call it 1. Okay, so condenser alone 1. We can see G1 equal to L0 plus T. We just make a note for our understanding that this is a total condenser. We discussed about this just a minute ago. So we have total condenser. G1 equal to L0 plus T. So this is moles per second. And we have G1, Hg1, incoming enthalpy, equal to L0, HL0. All right, so this is the liquid which goes back to the distillation column as a reflux from this separator. So L0 plus HL0 plus we have DHD, DHD, and plus, make a note, we have this QC, calorie per second, the heat load on this condenser. So this is enthalpy balance. Okay, we can write now QC as net load of the condenser as D. So we are just trying to rearrange this, R plus 1 Hg1 minus R HL0 minus HD. All right, so all we have done, we have made use of this fact that reflux ratio as we defined earlier is L0 by D. So we have replaced L0 RD. As an exercise, you can convince yourself that we can calculate the net load of heat if we know the reflux ratios. What is the product out here, D, and the enthalpy of the different streams, HD, HL0, etc. One can calculate the net load of the condenser. So that's 1. Let's make balance on 2, which is, let's say, it's total. All right. So to do that, recall we have the vapor liquid which goes out here. Let's complete this. We have this now QB, heating load, and we have the vapor which goes back to this. We have the bottom product as W, we have HW, and we have this XW. All right. So we have feed entering here F, XF or ZF. All right. The reason why we write ZF is ZF could be XF if the feed is liquid, or this could be YF if feed is vapor, or this could be a combination of liquid and vapor. So all possibilities are here. We are writing F in general ZF, and we have this HF. So this is a coordinate or the specs. These are the specs of entering feed here. We have W, XW, HW, XW here. Heating load is QB here. So now we make a total balance. We can also write F equals D plus P. So feed here, D here, and we have now this W, or we can call it B here. So let's change this to B. So we have F W plus P. Okay. Heat load, enthalpy balance, if we make energy balance F HF, so incoming enthalpy, plus we have this load of QB. We are supplying this QB into this reboiler to vaporize this vapor to this distillation column. So we have FHF plus QB. This will equal to all heat loads, which are all heat streams which are leaving the distillation column, including this QC plus WHW, WHW plus DHT, DHT, which means QB. Now we can write as reboiler load equivalent to this QC calculations. We have this QB reboiler load as DHT plus WHW plus QC, okay, minus FHF. So we have come out this expression for QC and QB by very simply, taking this total energy balance. Let's do one more time. So let's redraw this distillation column again here. We have the vapor which leaves here is condensed, right? Then we have this separator. We draw this product D, ZD, XT. This goes back to this top of this distillation column. First plate is 1. So we have this L0, X0, HL0. We have this QC as heating load. Feed enters here F with ZF and HF as its specification here. Let's take nth stage here and make a balance like this. So this is the envelope 3. So we had 1 for the condenser, 2 we made for the total column, 3rd is for this condenser. Now this vapor which arrives here is Gn plus 1, we have Yn plus 1, and we have this Hgn plus 1. Alright. The liquid which leaves the plate is Ln, HLN and Xn. Okay. So we can write Gn plus 1 incoming stream molar flow rate will be Ln outgoing stream plus the product D. That's 1. Similarly, we can write Gn plus 1, Yn plus 1 equals Ln Xn plus D Zd. This is 2. This can also be rearranged as Gn plus 1, Yn plus 1 minus Ln Xn equals D into Zd. See, notice why there is a reason why we have written like this. See, these are general expressions for any stage in enriching section. So we have taken this envelope just underneath this nth plate, where we can write that Gn plus 1, Yn plus 1 incoming minus outgoing for any plate from 1 to n in the enriching sections equals the output, which is a constant, d into z. Constant in the sense that this is specified. So once we specify the quality of the feed, quality of the product, distillate, and the molar flow rates, the difference between the two streams anywhere, choose any stays, make a note that this minus this is a constant here. We call it net rate of flux of A. Okay, so it's a net rate of flux of A moles per second, right? And the reason that why we write like this, if we recall that now we can apply this mixing rule. Since D is fixed, all it means for any stays in the enriching sections, if we apply this mixing rule on this HXY diagram, all of this will be intersecting at one point. In other words, if we take this vapor and recall we extract this liquid, we will get this D. And the second stage, if we take vapor, extract this liquid, you will get this D. We'll come back to this. So whatever we have learned for a single stage in drawing those operating lines, one can also make use of this, that the difference between the two molar flow rates at any stage, at any stage of the column remains the same as dZt. We can do the same thing for the enthalpy. G n plus 1 H G n plus 1 equal to ln HLN plus D HD plus QC. So the incoming enthalpy equal to 3 outgoing energy calorie per second. One is with the liquid, one is with the product, and one is this QCs. And again we can rearrange to write that the difference Gn plus 1 minus ln HLN is constant as D HD, saturated enthalpy of the living product, plus QC by D. Okay, so we have the similar situations of this mixing rule here. For any stage, either you make a species balance or you make an enthalpy balance. The difference between the two streams, vapor and the liquid, is a constant here, dZd and dHd plus QC by D. And this is very useful that we understand this, so that when we do the calculation graphically, when we represent, we understand that the coordinates of 1, 2, 3 will be on the same straight line because of the mixing rules. Okay, we also can rearrange to show that now we have ln over Gn plus 1. The same message we are saying that ln over Gn plus 1 can be written as Zd minus Yn plus 1 over Xn minus Zd equals Q prime minus H Gn plus 1 over Q prime minus H ln. So this Q prime now we are defining as Hd plus Qc by D. Now let's try to understand what it is. Living stream has the enthalpy only Hd with the molar flow rate D. All we are saying that now there is hypothetical stream whose molar flow rate is still the D moles per second, but its enthalpy is actually Hd plus Qc by D. So we have a hypothetical stream leaving this distillation column or this condenser. The molar flow rate is still the D, but it leaves with enthalpy Qc by D. We will make use of this to mark this point corresponding to this Q prime here. Okay, so the idea of doing this is the same here, that we have 3 points if we want to mark on HXY diagram. One is ln with species with constant mole fraction Xn, HLN. Second stream is Gn plus 1, Yn plus 1, Hn plus 1. And the third stream is D with the mole fraction Zd, and the enthalpy is Q prime, which we define here as Qc by d plus Sd. These 3 points for any tray 1 to n in the stripping in the rectifying section will lie on one straight line, because this is what we have done in case of mixing balance. This d is nothing but difference of Ln and Gn plus 1. Similarly, this difference of the two enthalpy HLN Hn plus 1, we can show that this is Q prime here. Okay, we multiplied by this molar flow rates. So if you mark these points on HXY diagram, these 3 will be on the straight line, as if from this point, if we subtract so much of enthalpy, we get this. Or in this liquid, if we add so much of this, we get this. If we add so much of enthalpy, total energy, we will get this point. It's all about mixing rule, which we have discussed earlier. We would like to plot this before we end here. So one can plot this. HXY diagram. So we have this HL and we have this HV. So what we have here, Ln over Gn plus 1 is Q prime minus Hg. Mark this point and call it, let's call it del D. Now look at the mole fractions here. This mole fraction is starting from the end, we have this Y1. Mole fraction of the stream leaving the distillation column is Y1. It's condensed completely, so we have Zd, and sent back as a reflux, which we have X0. Since a total condenser, this Y1 will be same as Zd, will be same as X0. All right. If this distillate or reflux is saturated, then you can see that this line will fall here. We'll call it H, L, H, L, X0. Okay. What is this del D point? This is the point which is the difference of enthalpies or total energy of any two streams leaving that plate. So vapor and the liquid, which means if you want to draw Ln Gn plus 1, you will have a straight line where this will be Ln, we will have Xn, all right. We have this Hgn plus 1, and this will correspond to Yn plus 1. Notice the difference between the two will give you del D, which is nothing but the difference, enthalpy or the energy of leaving streams, which is Hd plus Qc by d. That's your Q prime. All right, so this coordinate is here, for this is your Hd plus Qc by d. It's very important that we understand that this is consistent with what we have written here because of this mixing rule. This vapor which arrives at nth plate and the liquid which leaves this nth plate, the difference between the two is same as what happens to this hypothetical fluid with a molar flow rate d, but the energy with Q prime. So difference is same. That means you can draw all lines here passing through this del D points. This would be L1, this would be G2. All right, this will be L1, this would be G2, this would be L2, then this would be G3. We are making this energy balance for Ln and Gn plus 1 here. Let's come back to the first tray of the distillation column. 1, the liquid which brought from the reflux has mole fraction X0 and HL0, and the vapor which leaves is Y1, right? And Y1 is same as X0 because we were using total condensers. All right. So if we start from here, then this is Y1. We locate this point as this. Now just underneath this, we have this Y1, and this is Y2, plate 2 here, and the liquid which leaves, this mole fraction is X1. For the top plate, Y1 and X1, they are in equilibrium, or these two streams are in equilibrium, which means if this is Y1, we can now draw a tie line. which will intersect here to give you x1. Now take x1 and connect this to del D, x1 to y2. That means this will be your now G2. All right, so this go back to this. The way we have written ln Gn plus 1, we can write L1 G2, we can write L2 G3, etc. to connect all these points here. We will last time we will redraw this HXY diagram for total condenser. So we have this HXY diagram. This is HV and this is HL. Okay, and we are talking of total condenser. So we have QC, the vapor coming from the top plate is mole fraction is Y1. We have HV, etc. And then we have this separator, and then we are withdrawing this product D, we have XT and we have HT, all right, and this reflux L0, X0, HL0 goes back to this top plate, which is say 1 here. So this vapor is same as this, and the liquid which arrives to the top plate is same as this liquid which comes out from this total condenser. Okay, so since it's a total condenser, we have X0, XD and Y1 same. All right, so X0 equal XD equal Y1. So let's mark the different enthalpy and XY coordinates here. So we start with, we have this X0 same as XD same as Y1. So this point would be HG1. All right, so this HV is nothing but HG1, and we have the difference point del D here. So this del D is nothing but the ratios of L over this D. All right, so all we are saying that L0 over D is same as the reflux ratio and same as Q dash minus HG over HG for the first plate, HG minus HD. Okay, so this is HG1 here, and then this del D is the difference point with the enthalpy, which we have this Q prime here. Okay, so we can mark that HL0, if it's saturated, is here, HL0. And now let's look at the top plate, this Y1 and this X1. All right, the vapor leaving and the liquid leaving, they are in equilibriums. So once we have this Y1, we have the first tie line as X1 or corresponding to this L1. Okay, so we know the difference point, we connect this as an operating line. So we get here Y2. Okay, Y2 will have another operating line intersecting here, which is now X2. So again we connect this X2 to this HWD. So all right, so all we are saying here that once we know this difference point del D, then we can connect X1, X2, etc. with this difference point here to obtain the other coordinates on this vapor phase here. Okay, so this is about the total condenser when X0, XT and Y1, they are the same here, and the enthalpy HL0 is same as HD. All right, and they differ from HV because of this QC. So this del D, which we have the difference point, has this enthalpy of or energy of Q prime, which is QC condenser load plus HD over D. So the important point here to note is the way we are drawing this stage 1, stage 2, which are the tie lines, the vapor leaving the first plate and the liquid leaving the first plate, they are in equilibrium. So we have this tie line here. The second plate, the vapor leaving the second plate and the liquid leaving the second plate, they are in equilibrium. So this is the second tie line, and the one which we joined from here from X1 and x2 to this del D point, that gives you the operating curve here, which means that gives you the concentrations between the liquid which vapor which arrives here and the liquid leaves here, all right. So, this would be your connection between x2 and y1. So, notice this nomenclatures, we have this y1, we have x1, we have y2, we have x2, all right. So, x1 to y2 we have operating line, x2 to y3 we have this operating lines, okay. So, this is about total condenser, and similarly we can have we can mark the hxy point on the partial condenser, which we will do in the next class, okay.